Okay, good morning, good afternoon, and good evening. Welcome to the MOF 2024 webinar series. Today, we are going to have the third webinar. Before that, please allow me to give you a brief introduction about MOF 2024, a nice international conference on metal organic frameworks and open framework compounds. This conference will be held in Singapore July the 15th to 19th, 2024. Here is a brief history about this conference. This conference is the focus on recent advancements in metal organic frameworks, MOFs, covalent organic frameworks, COFs, and other porous materials. It is the most well-established conference in the field, with close to 2 decades of history, starting back in 2008 in Germany, and then 2010 in France, 2012 in UK, 2014 in Kobe, Japan, 2016 in Long Beach in USA, 2018 Auckland, New Zealand, 2020 online due to the COVID-19 impact, 2022 Dresden, Germany, and MOF 2024. This year will be held in Singapore. We are very proud to be the host for the MOF 2024. Singapore is a small city, but it's full of opportunities and excitement. So here you can enjoy not just the natural beauty, but also the modernization and great food. And we have beautiful beach and a zoo. It's both good for science and also for family time. So we have the following 5 major conference themes and topics. Materials, that is a focus. And we are going to discuss the fundamental phenomena and the properties of those materials, the synthetic methods of the materials, and their characterizations. And last but not least, we're interested to look at the applications and industrial integration of those materials. This conference is hosted by MRS Singapore, and it will co-hosted by NUS, National University of Singapore, NTU, Nanyang Technological University, the SUTD, the Singapore University of Technology and Design, and A*STAR, Agency for Science, Technology, and Research. Here are the conference schedule and the dates. So we have a 2-day pre-conference on July the 13th and 14th to be held at the NUS campus. And the main conference will start on July the 15th and will last for almost 1 week. The 16th and 19th will be the main conference, and the closing ceremony will be held on July the 19th. So we have a target about 1,000 participants, including 8 plenary talks. We have Professor Suzumu Kitagawa from Kyoto University and Professor Omiyagi from UC Berkeley as our special speakers. And besides, we have 6 other plenary speakers. We have close to 100 keynote speakers and invite speakers. And we have about 200 oral presentations. And we have a plan for more than 650 posters. That will add up to close to 1,000 participants. We have both the main conference and the pre-conference. In the main conference, we will organize forums for editors and forum for industry, so that the publisher and industry partners can also join. And we will organize gala dinner and social visits. So I want to use this opportunity to introduce some of our social visits. So after the pre-conference, which will be on the 14th of July, 2024, we'll have 1 social visit where we will provide a 1-way transport from NUS to Gardens by the Bay, which is a very beautiful garden close to the Sands Hotel. So you can enjoy the beautiful flowers and the trees. And on the first day of the conference, before the conference start, which is in the afternoon, in the morning, we have arranged the social visit 1, and that will include the Singapore City tour, plus Marina Bay Sands Sky Park observation deck. So I believe for some of the participants, this might be your first time to visit Singapore. So you don't want to miss the opportunity of the social visit 1, where you can enjoy the history of the city and the beautiful architect and all the other stuff. And if you have family members, feel free to bring them as well. Okay, so this social visit will be held on Monday from 9:30 in the morning to 2:30 in the afternoon before the registration. The fee is Singapore $80 per person. So we have another social visit that is after the main conference, where we will show the probably the first MOF-based carbon dioxide capture plant at Tuas. This will be the first in Singapore. It will be on Friday, July the 19th, from 3:30 to 6:30. We will provide a complimentary with two-way transport between the conference center and the carbon capture plant. The gala dinner will be held on Thursday, 18th July 2024, from 6:30 to 10 p.m. It will be held at Carlton Hotel, Singapore, where you have the chance to enjoy not just delicious food, but also very good discussions, because Professor Omoyagi will give a special presentation during the gala dinner. We understand that traveling to Singapore for some of you might be challenging because especially if this is your first time to visit us. So here in the conference website, we have provided all the accommodation information. You can feel free to refer to the conference website for more details. Basically, we list all the hotels close by with their address, with the star level, and the distance towards the conference center and the price. So if you have made your mind to join us, please book your hotel as early as possible. So here are some important dates. The abstract submission deadline actually is the end of this month. So we only have about 2 weeks left. So please submit your abstract as soon as possible. And you will be notified about your abstract submission outcome in March 2024. And then we recommend you to finish the registration as early as possible, because the early bird registration deadline will be in the middle of April. So please join us by looking at the conference website, or you can follow us through the social media like the Twitter or the WeChat. Before today's webinar, please allow me to give an advertisement for our next webinar. The next webinar will be given by Professor Catherine Mircea from Dartmouth College, and her presentation title is The Molecular Engineering of Conductive Framework Materials for Chemical Sensing, Filtration, and Detoxification. So it will be held on February the 6th. The Singapore time is 8 p.m. Okay, so please register. So that's all. Without further ado, please allow me to introduce our first speaker, Professor Mircea Dincă from MIT. So Mircea was born and raised in Romania, and he was educated at Princeton University and UC Berkeley, where he got his PhD in 2008. He started his independent career at MIT in 2010, where he is now the Keck Professor of Energy and Professor of Chemistry. His research focuses on understanding and manipulating the physical properties of metal organic frameworks especially electrically conductive MOFs, and on exploring the potential of MOFs for catalysis. So without further ado, Mircea, the floor is yours.
All right. Hi, everyone. Thank you, Dan, for the introduction and for the opportunity to speak to so many people at once. I hope to see many of you in Singapore. It'll be my first time, so I'm looking forward to that. Today, I'm going to tell you very briefly about how my group and ourselves think about the potential of MOFs in catalysis and also small molecule reactivity. And I'm going to start by trying to do a little bit of a comparison, really, between MOFs and enzymes. I know many people in almost any catalysis field take inspiration from enzymes. So you might think that it might be a little bit of a stretch to compare MOFs to enzymes, but bear with me because I do think that MOFs, at least functionally, have something to say in terms of their similarity to enzymes. So if you think about enzymes and what makes them good for many of the reactions that they do is that the metal parts, metal active sites in the enzymes are surrounded by weak ligand fields. And that means that you have high spin configurations. Often those means those are better for both oxidative and reductive processes. And so what are those ligand fields in enzymes? They're things like carboxylic acids, amino acids, histidines, so basically imidazoles, phenols, thiols, and so on. So those are not just similar, but are actually identical to the types of ligands that you might see in MOFs. So even though structurally they're not necessarily similar, you might expect functionally to have similar reactivity to enzymes. Site isolation is certainly one of the premier things that makes enzymes selective. And you might say that they're the ultimate site isolated catalyst because the one active site that each protein has will never see another active site. And I think this is exactly what MOFs can do very, very well. On the background here, you can see a metal in pink that is spatially isolated, so basically site isolated from any other metal in that MOF. That's important, of course, because it eliminates all sorts of deleterious reactions, and the lack of site isolation is really what makes one of the primary reasons that molecular homogeneous catalysts eventually die. Multiple open metal sites, I do think this is actually unique to MOFs. Again, I'm going to point you to this pink atom in the center. It has 4 open coordination sites, and that's really difficult to do both with homogeneous and even other heterogeneous reactants or catalysts. And obviously, if you're trying to do catalysis, you want to have at least one open metal site for substrate binding. But there are certain features that enzymes do have that MOFs do not. So are MOFs dynamic like enzymes? Enzymes have to be dynamic. Often the selectivity comes from that dynamic motion. Are they tunable rationally? Many of us like to think that we are rationally designing MOFs, but they are self-assembled materials. So we're only empirically deciding or figuring out what we're actually going to make, but it's not truly rational. Finally, do we have, or not finally, but next, we have unique reactivity. If we're building this up as a unique sort of framework for exploring chemical reaction space, what kind of reactions can we do? What kind of catalysis can we do? And then fourth and final, are MOFs actually stable to water? This is a question that perhaps in this audience need not be answered, but outside of this audience, there's this perception that MOFs are completely unstable to water or largely unstable to water. And there is a kernel of truth, as we all know about that, but we should also understand what makes some MOFs unstable to water and how can we make MOFs stable to water. So I'm going to go very basic here and say, of course, MOFs are made from SBUs and organic ligands, but really I would argue that the most important connection in any MOF is the metal ligand connection. That is the weakest bond. It's what defines the thermal and hydrolytic stability of MOFs. So if you look at a zinc-oxygen bond, it's actually a very ionic bond. It's going to be very hydrolytically unstable. How can we make that bond more stable? And what we need to realize really is that MOFs, all MOFs, are actually metastable materials. as long as just like any other porous material, there is always going to be a dense phase that is going to be much more stable, or at least somewhat more stable than the porous phase. So all MOFs are metastable materials. There's nothing wrong with metastable materials. They can be very metastable, if you will, because they then have a very large activation energy to going to that undesired dense phase. In other words, we can make MOFs very kinetically stable. And those MOFs that are actually stable to water, or are known to be stable to water, are kinetically stable to water. Okay, and so basically then, if we understand that, how do we make something more kinetically stable? It could be as simple as looking at a graph that I often show in my freshman chemistry class that says, okay, what is the self-exchange rate of water from a ligand to a solution, or vice versa? And what you'll find is that even within the divalent metals, which are often the majority of metals used in MOFs, you'll have copper 2, manganese 2, iron 2, zinc 2, nickel 2. You can see the difference in kinetics between nickel and copper is almost 6 orders of magnitude. So that means that if one copper-based MOF is stable for 1 second or 1 day, the nickel version of the same exact MOF will be stable for 1,000,000 days. And that is sufficiently stable for all of our lifetimes combined. And so really choosing the right metal for making a stable MOF is going to be very important. Even zirconium MOFs that are touted to be very, very water stable, I would argue are still kinetically stable, because the zirconium oxygen bond simply means that it, as far as comparing it to, say, a zinc oxygen bond, both the dense phase and the porous phase are lower in energy, which automatically makes a kinetic barrier higher. Okay, so we can make water stable MOFs, which for catalysis is very important. Are MOFs dynamic? I will give you just one simple example from my own lab, where we demonstrated that MOF5 itself, which everybody knows, and that as having sort of pseudo-tetrahedral zinc sites, is actually very dynamic at the metal site on a time frame that is not actually reflected in techniques such as X-ray diffraction, but can be seen with NMR spectroscopy or MD simulations, and where basically it says that the zincs are not entirely tetrahedral, and they can become 5-coordinate or even 6-coordinate by binding of DMF solvent. And that enables something very important that my group takes advantage of a lot, which is metal exchange. You can literally exchange metals from the solution to the SBU. So now you can rationally tune the composition of MOF by saying, if I take a metal node, an SBU, and it is naturally self-assembled with manganese or zinc or copper, what have you, but I like that metal center because it has, say, 2 open coordination sites or maybe 3 open coordination sites, but I'd like to have nickel there or titanium or chromium. All I need to do is actually just make the initial MOF, make the parent MOF from whichever metal it likes to be made from, and then exchange that metal with something else, with titanium or chromium or whatever I like for my catalysis or desired reaction. So basically, this opens up in a very rational way, because I know exactly what the structure will be, a huge compositional space and a huge sort of framework for studying reactivity and catalysis with these materials. So I'll give you 2 examples of how we can take advantage of this compositional space. One, we can isolate reactive intermediates that are relevant for catalysis. So this would be for fundamental studies. And then we can also ask catalysis questions that are challenging for other heterogeneous systems, such that MOFs are not necessarily replacing other catalysts, but are actually providing a complementary opportunity for heterogeneous catalysis. So this site isolation, as I mentioned, will enable the formation of very reactive intermediates or even unique reactivity at the metal nodes. And the one example I'm going to tell you about is something we published very recently, but on a material that I actually made as a graduate student myself. And this was a very interesting material where the SBU is a manganese 4 cluster with a chloride in the middle between the 4 square planar manganese. So the chloride itself is actually kind of interesting. It's a square planar chloride. You don't see that every day. But what we found is that as you activate this material, basically trying to remove the solvent, as many of us do when we measure, say, adsorption isotherms, we found that just soaking the material in methanol removes some of the chloride along with charge balancing manganese from this structure, thereby leaving an empty square planar manganese 4 cluster. So we naturally thought that since manganese is so redox active, it might actually react with something like oxygen. And what we found is that indeed from the original material, which is all manganese 2 and therefore colorless, simple exposure to oxygen immediately colored the material into this deep purple. You can do vibrational spectroscopy. I don't have the time to go through this, but you can label the oxygen that you react with your manganese MOF, and you'll find that what you make is actually breaking of the O2 bond into 2 dimuoxo compounds. So basically, we're activating O2 in making 2 oxo compounds, thereby oxidizing the manganese 2 to manganese 3. What was even more interesting is that if you heat the material, you actually make O2. This is extremely unusual and extremely difficult to do for any material, homogeneous or heterogeneous, and it is indeed what gives rise to life on Earth, incidentally, I would say coincidentally, also through a tetramanganese cluster in photosystem 2. So making this OO bond has specific spatial and electronic requirements that this MOF enables because of its site isolation. What about catalysis? So catalysis, then you can ask, well, what are the questions that we can answer with MOFs in catalysis that other heterogeneous catalysts can't do? And what my group is interested in is in commodity chemicals. MOFs have small pores. They can't fit very large substrates, but commodity chemicals have a lot of problems there are a lot of problems related to commodity chemical production in heterogeneous catalysis. One of them is the production of 1-butene from ethylene. This is a huge industrial process done on almost 1 million metric tons per year. And you would think that the industrial catalyst, which has a turnover ratio or turnover frequency of 100,000 per hour, pretty selective for 93% butene, has only half-hour half-life. That's not the problem. What the industry cares about is that 7% of this high-purity ethylene used is actually going into unproductive process, which is polymerization rather than dimerization. So we said, can we actually engineer a catalyst within a MOF that is similar to a known homogeneous catalyst and that can benefit from site isolation? So long story short, for many processes in catalysis, we believe we don't actually need to make new MOFs. There was a MOF already made. It's called MFU4L. It was originally made with zinc, but with our cation exchange strategy, we can implement it with nickel. And now the nickel MOF SBU has exactly the same structural features as the original molecular catalyst, but it works better because it's spatially more open, and that actually enables better selectivity than the molecular catalyst. So it turns out that this heterogeneous catalyst is better than the homogeneous catalyst and better than the existing industrial catalyst for this reaction. Okay, it has turnover frequency that is competitive with the commercial catalyst, but it has much higher selectivity, close to 98.5% for 1-butene, with the balance being almost entirely hexene, so no polymerization whatsoever. And this is exactly what the industrial need for this reaction was. So I'm just going to finish here, leave time for my colleagues, but I want to leave you with this thought that at the SBU, there is an immense potential for doing reactivity that has not been possible with heterogeneous or homogeneous processes because we have site isolation and because we have multiple open coordination sites. As far as what problems we can address, there are many problems in heterogeneous catalysis for the formation of commodity chemicals, carbonylation, hydroformylations, hydrocyanations, all sorts of selective oligomerizations. Connie, who's going to speak later, worked on this as well. And also, just from a fundamental perspective, there is really cool chemistry to be had in taking advantage of site isolation for for reactive intermediates and for small molecule reactivity. So I'll be happy to answer some questions after the other two speakers.
Thank you very much, Mircea, for this exciting, excellent talk. I'm sure there are many, many questions from the audience, but right now, let's just hold on the Q&A. We have two more speakers, and after all the presentations, we will have the Q&A together. Okay, Mircea, thank you very much. So let me introduce our second speaker, Professor Phillip Milner from Cornell University. And Phil completed his PhD with Professor Stefan Buckworth at MIT, where he worked on the palladium catalyzed fluorination and cyanation chemistry. And his postdoc research with Professor Jeffrey Long at UC Berkeley focused on the design of amine functionalized MOFs for carbon dioxide capture. So since 2018, Phil has been a member of the faculty at Cornell University, where his research program bridges organic, inorganic, and materials chemistry with an emphasis on the design of MOFs for catalysis relevant to the synthesis of complex drug-like molecules. And his research has been recognized with a number of awards, including the NSF Korea, the DOE Early Career, the NIH MIRA, and the Camille and Henry Dreyfus Teacher Scholar Award. So without further ado, the floor is yours.
All right, thanks. Thank you, Dan. All right. Thanks for that introduction, Dan. I'm excited to tell you all today a story about how we can use MOFs to tackle a challenging reaction related to the synthesis of complex molecules, a very different target area than what Mircea talked about. And I think MOFs have really a lot of potential in this underexplored space. There's two ways we think about MOFs potentially being useful for catalysis. What Mircea had really talked about, and I think what Connie's going to talk about too, are thinking about MOFs as these really tunable reactors where we can build in active sites that are difficult to replicate in solution. But what I'm going to talk about today is a different way of thinking about MOFs, more as reagents, where we can use their, take advantage of the pores of these materials to actually stabilize reactive species that might be really difficult to work with in the laboratory, and enable us to discover new reactions that would be hard to find otherwise. And so what has driven inspired a lot of the research in our lab is the synthesis of complex molecules, particularly fluorinated molecules. Fluorine is everywhere in the pharmaceutical industry and in agrochemistry, material science, polymer chemistry, it's everywhere. And yet the installation of fluorinated functional groups, in particular fluorinated alkenes, like these here, remains quite difficult. And so you can see that if you look at, for example, the synthesis of this antiviral compound here, to install this really simple looking difluorovinyl group, it took multiple steps from commercially available starting materials. And what we thought is that there's a much simpler disconnection we could make here. What if we break this bond right here and just install that functional group that way? So on one hand, that produces a starting material that's totally fine, but on the other side is this compound vinylidene fluoride here. Now, this actually seems very attractive as a synthetic building block. It's quite cheap. It's a monomer used to make polymers, PVDF. And all of these simple fluorinated molecules here are actually commodity chemicals that are relatively inexpensive. But they have one serious drawback that makes them difficult to use for reaction development, which is they are gases. And they're not only gases, they are all pretty potent greenhouse gases. They tend to be toxic and flammable as well. So developing synthetic methods using these types of small molecules is quite difficult to do. If we think about how we're going to do reaction development with these exotic gases, we can either use them directly, which can be as simple, just filling up a balloon with the gas, or as complicated, very lots of blank lines and all kinds of setups as we want. But either way, it's very low throughput. And it can be hard to develop transformations when you only can set up one at a time like that. We can also generate the gas in situ. but this has a lot of drawbacks. You have to come up with a new way to do it for every single gas, and it may or may not be compatible with the reaction you're trying to do, but it is higher throughput. Our idea was to take advantage of the porosity of MOFs and load up these kinds of fluorinated gases into these materials, which would allow us to handle them as solid reagents in the laboratory. This is nice because it should be universal. We can do this for any gas we want. These MOFs, of course, are heterogeneous. They're insoluble in organic solvents, so we can just filter them off when the reaction is done. We could actually weigh out the solid and add, say, 1, 2, 3, 4 equivalents of gas, however much we want. And I'll show you how that can be an advantage in just a bit. And it also enables us to set up tons of reactions and do high throughput reaction development with gases. So when we tried to figure out what was the best MOF to bind these types of fluorinated gases, which hadn't really been explored, Mary started by looking at measuring uptake of this gas, vinylidene fluoride, here in metal organic frameworks. To do that, we measure these, what are called gas absorption isotherms. Probably almost all of you have run one of these before, if at least a surface area analysis, where we look at varying the pressure here and the uptake of the gas, and adsorption in closed circles and desorption in open circles. And so by looking at a bunch of different materials, Mary was able to kind of benchmark them, their ability to bind vinylidene fluoride. And what we compared was their storage capacity for the gas, which we want to maximize to minimize the amount of MOF we need to deliver the gas. And also the binding strength, the enthalpy of absorption, which we want to maximize so the gas doesn't just leak out of the MOF before we want to actually use it in a transformation. And she found that this magnesium-based MOF, magnesium DOBDC, also called magnesium MOF74, probably many of you are familiar with it, was actually the best in terms of binding vinylidene fluoride with a high capacity and relatively strong binding. And I think what's remarkable about this approach is the significant volume compression that happens inside of MOFs. So we can store 1 millimole of gas, which would normally be a relatively large balloon, 23 milliliters, in just maybe 100 or so milligrams of MOF, or 0.1 milliliters of solid. This MOF is nice because it actually binds a range of fluorinated gases quite strongly. Mary showed kind of over the course of her PhD, this seems to be a universal thing, that this MOF is particularly good at binding fluorinated molecules with strong enthalpies of absorption as well as high capacities. So here's why it's so good. This is the structure of this MOF. And so it has hexagonal pores here that are going into the screen, and it's kind of like a honeycomb in the plane of the screen here. Here's the linker of this MOF, but what really sets it apart, I think Mircea mentioned these open metal sites, is that this MOF has a very, very high density of these coordinatively unsaturated metal centers, in this case, magnesium sites that are missing an axial ligand. And if we dose them with the fluorinated gas, we were able to show by powder X-ray diffraction that they actually bind to this relatively strong magnesium fluorine interaction here. We can also support that by solid state NMR as well, where we see, when we look at the free gas here, and we dose it into the MOF, it shifts upfield from the shielding effect of the linkers, and it broadens because it's now immobilized in the MOF. So both of these techniques show us this MOF has a very strong interaction with this fluorinated gas. Now the question is, can we get it back out? And so what Caitlin did was try to see if we could load up a gas inside a MOF and then release it into solution by just dropping it into solvent and looking by fluorine NMR to see if the gas came out. And in fact, we were able to see that it comes out quite quickly from this MOF, regardless of the polarity of the solvent we use. It saturates the solution in about 10 minutes. And so we have achieved at least a goal of being able to handle a gas as a solid and throw it into a reaction. But we wanted to see if we could do even better than this. Can we actually control exactly when the gas is released into solution, which would be even better for being able to set up reactions. So what Caitlin found she could do is take this gas-loaded MOF and actually pack it inside of a little sealed wax capsule, which protects it from air and moisture here. And now you can toss that capsule into solvent, and after an hour, we don't see any gas in solution because it's impermeable to the solvent. But she found that if she just sonicates it, the capsule breaks open, the MOF falls out, and then the gas is released into solution, and you can saturate it pretty much on demand by sonication. So I'll take you through now in the last portion of my talk some of the reactions we have found using these gas-loaded MOFs. We were really interested in using vinylidene fluoride as a universal kind of building block to make any kind of fluorinated alkene that we could. And what we found very quickly is that this gas is surprisingly electrophilic and engages in deep fluorinative couplings quite easily here, where we can actually see that with using a simple palladium catalyst here, we can actually couple vinylidene fluoride with boronic acids to make these alpha fluorostyrene analogs. And these gas-loaded MOFs are actually quite stable here. So we found that if we left the gas-loaded MOFs out in the kept them cold or in air, they do slowly lose the gas. But if you look at these capsules here, they actually don't lose the gas even after 60 days. So you can really think of these as just a little cylinder that sits on the bench top loaded with gas. I'll just show you a couple more transformations we have found using these gas releasing reagents here. So we found that for vinylidene fluoride, we can also deprotonate it using S-butylate transmetallate to zinc to make the zinc reagent here, which engages in a palladium catalyzed Negishi coupling to make these beta-beta difluorostyrenes here with a pretty good functional group scope. So this is a way that we can actually functionalize both ends of VDF, either this carbon or this carbon. We also were able to use trifluoropropene here to do a Heck-like coupling to make these trifluoromethylated alkenes, trifluoromethyl iodide to make also trifluoromethylated compounds under these Svensson-like conditions. And what we have started to do now is use this platform as a way to explore the reactivity of gases that have really been overlooked in the synthetic community. So for example, Caitlin, as I mentioned, has found that vinylidene fluoride is surprisingly electrophilic. Well, it actually reacts with a range of nucleophiles, not just palladium catalysts, but also nitrogen heterocycles here, which allows us to actually make a range of different N-fluorovinylated compounds here, even from some particularly large and complex molecules here, using these very simple metal-free conditions. And these products themselves are quite useful. They're interesting on their own, but they can be derivatized to make fluorinated cyclopropanes with heterocycles on them, which I'll just tell you is a buzzword salad of things that medicinal chemists love, all three of those kinds of functional groups. And so it also works for other types of fluorinated alkenes like hexafluoropropene. And one thing I just want to note about the advantage of this approach compared to just using gas-loaded cylinders is Caitlin found hexafluoropropene is particularly electrophilic, and you can get polymerization or oligomerization here. But she found that, for example, you can solve it in some cases by adding the gas-loaded MOF slowly to the reaction in a couple portions, which is not something that would be very easy to do with the gas itself. And so we think this is really enabling us to find new reactivity that would be hard to identify using, say, balloons filled with gas. So with that, I just acknowledge my group, the folks who did this work. This project has been led mostly by Caitlin, along with Emily and Jaewon. And of course, thank all of you for having me, and I'll be happy to answer any questions during the Q&A afterwards.
Thank you very much for this exciting result. All right, so let's move on to the next speaker. Last but not least, we have Dr. Constanze Neumann from Max Planck Institute. So Connie, she obtained her PhD with Professor Tobias Ritter at Harvard University, where she developed methods for installing radioactive fluorine isotope into arenes and performed the mechanistic investigations into the conservative nucleophilic aromatic substitution. She did her postdoc with Professor Mircea Dincă at MIT on the development of MOF-derived catalyst for the upgrading of alcohols. And she's now a Liz Meitner group leader at the Max Planck Institute for Kornforschung, working on MOFs and annoying nanoparticles catalysts. Her group is interested in studying how new reactivity can be enabled by the MOF structure's ability to control the distance between adjacent metal centers. So without further ado, Connie, the floor is yours.
Okay, thank you very much, Dan, for the kind introduction and also for the opportunity to be here today. And similar to the last two speakers, my group is very interested in seeing how we can develop reactivity with MOFs that we can't already readily access with molecular catalyst or classical heterogeneous systems. And I want to tell a story today about how we go about and identify potential opportunities for such MOF catalysis. And one thing that we found that was very inspiring to us was the reactivity of rhodium-2 metalloporphyrins, because there are some individual reaction steps that are extremely powerful that rhodium-2 metalloradicals can carry out, such as the activation of methane at room temperature, where there's only 1 bar of methane present. But then, despite a significant amount of work, there hasn't been any catalysis developed based on these individual steps, not even a stoichiometric transformation, because if an oxidant is added along with the methane, you don't actually get any oxidized products, but instead you get these rhodium-3 carbon-bound intermediates that are thermally very stable and obstruct catalytic turnover. And even if you go to much simpler systems, such as hydrocyanidation, for example, a standard reactivity for rhodium catalysis, then instead of observing hydrocyanidation reactivity, you see very rapid splitting of the silane to make rhodium-3 intermediates, and also reactivity of the olefin with 2 rhodium centers, so that you once again have rhodium-3 centers that don't react any further in the catalysis. So if you have both reagent present, you don't obtain any hydrocyanidation with the molecular complex, but instead you get these rhodium-3 compounds. And one approach that often is very beneficial in homogeneous catalysis is that you simply increase the steric bulk around the reaction site in order to shut down some processes that would be destructive. For example, dimerization of the complexes via rhodium-rhodium bond formation. That's something that you can readily inhibit by just having bulkier substituent. So while this complex dimerizes in solution, once you have steric bulk on the ligand set, you get this complex monomeric in solution. But once you add ethylene to it, it very quickly reacts with 2 rhodium molecules reacting across the ethylene to make rhodium-3 intermediates. And even if you increase the steric bulk further and even further, you still cannot shut down this dimeric reactivity. So we thought that maybe instead of steric frustration, we have geometric frustration present in the MOF that would not allow the rhodium centers to actually react across the ethylene center, and so that they would have to engage with the substrates in a new and different fashion, which would hopefully allow us to develop catalysis. And the nice thing about the MOF is that despite the fact that we can no longer have any processes that involve 2 rhodium centers reacting across the ethylene molecule, there's still a high concentration of rhodium-2 sites present in the molecule. So we figured that in order to access rhodium-2 metalloporphyrins in a metal organic framework, one good strategy towards that synthetically would be if we made a rhodium-3 methyl complex in the MOF, because it is known from homogeneous catalysis or chemistry that you can split the rhodium carbon bond using light, and the only molecule that's released here is methane, which means that that would translate potentially very nicely into a MOF system because you don't generate any problematic side products. So we were very happy that after a significant amount of optimization, we found robust syntheses that would allow us to access these rhodium methyl intermediates in 2 different zirconium MOFs, PCN222 and PCN224, so that we would have the ability to look at 2 systems that are made of the same building blocks, but where the rhodium sites are spaced in the different manners, which is something that is, I would say, relatively unique to MOFs, that you can actually investigate what the effect of the distance between the rhodium centers would be on catalysis to exclude, for example, any reactivity that relies on the proximity of 2 rhodium centers. And with that compound in hand, we were interested to see if we could use light, so in this case 390 nanometer light, to split the rhodium carbon bond and the rhodium methyl precursor in order to access the rhodium-2 metalloradical, and if that metalloradical would then be able to carry out catalysis. So the rhodium-2 and PCN222 and 224 was indeed able to furnish the hydroxylated product very efficiently. And when we look at the molecular model system in solution, that would correspond to the linker that we're using in the MOF, we only got 14% yield under the same reaction conditions. Then we figured maybe that's not a very fair comparison because this molecule can actually dimerize in solution. So the concentration of the rhodium-2 that would be available to carry out catalysis would be very low. So we used this system in which there's steric protection available, so that you actually have the rhodium-2 as a monomeric compound in solution, but that actually decreased the catalytic efficiency of the system. Whereas with a MOF catalyst, you can drop the catalytic loading in half and still get very efficient reactivity after 24 hours with over 500 turnovers. And while to us the most interesting system was ethylene, because it does not have any radical stabilizing groups present in the molecule, and it's the most simple and unbiased system. Due to the large pores that are present in PCN222 and 224, you can also use larger substrates, so different olefins are compatible, and you can also use different silanes. The reaction starts to fail, however, when the steric bulk around the silicon center becomes too large, in which case the rhodium no longer effectively interacts with it. And importantly, also after the catalysis is done and the catalyst is recovered, the rhodium sites remain well dispersed and the PXRDs look unchanged from the material that was present at the start, which increased our confidence that we were truly looking at the catalytic site that we had planned and not something that is a decomposition product of the original catalyst. And rhodium catalyst can also be recycled several times without any systematic decrease in the yields. We also looked at making larger MOF crystallites in order to confirm that the catalysis was actually taking place in the pore like we had imagined in the design, rather than simply on the surface of the material. And we don't observe any decrease in the yield when the crystallites become larger. So what was of particular interest to us is to see how the catalysis compares with what is going on in solution and the reasons behind that. So how is the MOF actually beneficial to the catalytic transformation? And the comparison that I showed you earlier was when we carried out the reaction under photochemical conditions. So at the very beginning of the reaction, if the rhodium methyl precatalyst is used, light is necessary because we have to split the rhodium carbon bond in order to generate the reactive rhodium-2 center. But for the MOF system, we can isolate that rhodium-2 site in the MOF, and that is then a stable material that we can store. And then we can carry out thermal catalysis of hydrocellulation, even at room temperature, with very slow reaction rates, but without any deactivation of the catalyst, so that over 200 turnovers can be achieved after 10 days. If we heat the reaction up somewhat, then synthetically useful yields can be achieved after a much shorter reaction time. But whereas the MOF catalyst can react efficiently at 70 degrees, when you look at the homogeneous catalyst, even at 140 degrees, less than 1% of the desired product were formed. And the vast majority of the catalyst actually gets converted into these rhodium-3 intermediates via transformations that are kinetically very facile and sufficiently thermodynamically favorable that even at 140 degrees, the free catalyst is not regenerated, so that the thermal catalysis of this reaction is essentially restricted to the MOF system, and the MOF is truly necessary in order to get this catalysis to work and not simply beneficial for it. But even for the light-mediated transformation, which can to some extent also happen for the molecular system, even if it proceeds at slower rates, we observe a significantly lower selectivity than we get with the MOF system, where we also get faster reaction rates. And to see if this is something that is essentially restricted to the hydrocellulation reaction, or if this is a more general platform that allows these metalloradicals to engage in catalysis, we also looked at hydrogermylation, which is a less investigated synthetic reaction compared to hydrocellulation. And we found that that can also proceed effectively with the MOF system. What was interesting here is that we saw a real step function in terms of the decrease of the reaction efficiency as the size of the molecule increases. So for these fluorinated arenes, the reaction was complete after 1 day, whereas here, with the addition of the O-methyl substituent, the reaction time increased to 6 days, right about at the time where the product of the reaction becomes large enough that it just about can still escape from the pores. And if 2 olefins are present, like in this case here, we get chemoselective functionalization of the terminal olefin, which is a nice feature that is synthetically valuable. And similar to the hydrocellulation reaction, also hydrogermylation can be carried out as a thermocatalytic reaction that even proceeds at room temperature. And to try and get some insight into the mechanism of that transformation and to see if it actually proceeds in the way that we had sort of initially planned, we set out and look at the mechanism with a team of fantastic collaborators so that we could look at it from a variety of different experimental aspects as well as from a theoretical point of view. And EBR was very helpful in that context because we could readily confirm that upon photolysis of the rhodium-carbon bond, we in fact get these site-isolated rhodium-2 metalloradicals. And we see that the breadth of the EPR signal changes significantly for the two MOFs because the distance between the two rhodium centers is varied as we go from one MOF framework to the next, so that we can modulate the electronic communication between those two centers. And what was nice is that upon addition of the silane, we could see the formation of a 3-center, 3-electron silane sigma adduct, which would not, the formation of which we've never observed in solution. And we believe that the reason for that is that in solution, if such an intermediate was formed, it would immediately be split by another rhodium-2 center that approaches the silane adduct and leads to the formation of rhodium hydride and rhodium silo. Whereas in the MOF framework, such intermediates can actually be stabilized, which is very beneficial to the catalytic transformation. And the intermediate could be further validated by high-score studies in addition with isotope labeling to confirm that it is really an interaction between the rhodium via the hydrogen versus the deuterium center. And after the sigma adduct is formed, it can then, under photochemical condition, be split to form silyl radicals, which are engaged in reactivity with ethylene. And both of these radical intermediates could be trapped in the presence of tempo. And the catalytic cycle in the presence of light is then concluded by the hydrogen that was positioned on the rhodium center in the first step of the reaction getting picked up again by the carbon center radical in order to close the catalytic cycle and reform the rhodium-2 catalyst, which was crucial to us because that is a mechanism that is also viable for a transformation that can proceed in the absence of light, which we observed experimentally. And with that, I would like to thank the people who contributed to this work, as well as the people who funded it, and our excellent collaborators that assisted us very vitally in our mechanistic work. Thank you very much for your attention.
Thank you very much, Connie, for your excellent talk. Now, may I introduce the other two speakers to come back to the Q&A. This will be the most exciting part. And I can see that Mircea, you're very effective in answering questions. There are already some questions that have been addressed. So that will make my pressure less. So I'll just read the remaining open questions. I can see that you are eager to answer some of them. So the first question, I'm just going to read from the top to the bottom, okay? So for the rest, for the audience, if you have other questions, please type in the question and answer chat box. So the first is Lincoln. And he asked in the electrocatalysis process, can you tell us more about the influence of the bond strengths implying the metal active site at the electrocatalytic interface during the electrocatalytic process?
Sorry, I was muted. Yeah, this one was too much to type. Thank you for the question. I mean, electrocatalysis is obviously a super wide topic in and of itself. And, you know, there are many people who focus on this. We did a little bit of work on that, but I think that the way to think about electrocatalysis is very different than, you know, really the topic of this webinar. And electrical conductivity is absolutely key for that. So I think that's something that, you know, you're better served either through a different webinar or maybe through the MOF conference itself.
That's a good suggestion. Next question from Hamed. He's wondering, is there any specific reason you have not focused on lanthanides compared to transition metals?
Very briefly, lanthanides obviously can be good in catalysis, but mostly for Lewis acid catalysis, right? Their orbitals are such that they don't really engage in inner sphere catalysis. And so it depends on what you want to do. Lanthanides may be useful.
Right. Next question from Shutin again for Mircea. This question is a little bit more technical detail. He's curious about the oxygen activation at the manganese 4 cluster. So the first process to soak the MOF in methanol at room temperature, remove the manganese dichloride. For H cluster 1, the copper MOF. He repeated the copper with the ruthenium metal, and there's 1 chloride coordinate with ruthenium center. So may I use the same method, remove the chloride attached to ruthenium?
One of the reasons that chloride comes out in our material is because it comes out as part of a manganese chloride equivalent. So I think it's really aided by that charge balancing cation. Different MOFs have different ways to be activated. I think it's hard to sort of generalize like that.
Okay, thank you. The next question, can a synthesis of MIPs, which I believe is a family of MOFs, in the presence of the quantity of the MOF zirconium affect the structure of the MOF in the composite material obtained? So who is interested to answer this question?
I don't know what an MIP is, I guess that's my question.
I think that's probably the series of MOFs synthesized by Christian from France, probably. But if the question can be more specific, I think we have a better answer for that. So I will skip that question. The next question from Sumanta, again for Mircea. Wondering if you could discuss a little bit about some fundamental aspect of those MOF-based catalysis, such as scalability and the cost effectiveness from the industrial point of view.
Yeah, a little bit. I think actually Phil would be just as good at answering this. But from my perspective, right, like there's a little bit of a misunderstanding when it comes to cost of MOFs. There are MOFs that are being produced on the ton scale right now for industrial processes. Of course, not all MOFs can be produced and they're not all cost effective. In fact, I think the ligand is often what drives the cost of a MOF. But it really, we should cut down on this, propagating this myth that MOFs are not cost effective.
Yeah, I agree.
Yeah.
I agree. It also depends on the process.
Can I jump into?
Maybe Phil wants to complete that.
I can add my 2 cents here, because I totally agree, and I think even for some of the stuff we've done for more towards the organic synthetic side, there the cost is almost, MOF is like much cheaper than most of the catalysts they use. So actually there you have a real advantage where this is not a problem at all. And I think in terms of the organic ligand, like Mircea said, process organic chemists are great at figuring out very cheap ways to make organic molecules. They just need a reason to do it. So as MOFs come online, people will figure out how to make the linkers much cheaper, and the cost will go way down, I think, for a lot of these. So I think it's something where we've talked ourselves into this loop of this being a problem, and I think it's very solvable. Depending, of course, if you're not making a palladium MOF or something, then you could really make it on reasonable scale. Even then, that's not really a problem. But yeah, so I agree with Mircea. I think this is totally a solvable issue.
Okay, great. So we have an anonymous question. Does the kinetic stability and the water ligand exchange rate of the MOFs affect their mechanism, for example, attraction to magnet?
I'm guessing this might be for me. I don't know. I mean, there's a lot of layers implied in this question as well. I think, something focused on the physical properties of MOFs might be a better venue for this. But very few MOFs are magnetic in the sense that they're actually attracted to magnets, if any, really. And so, yeah, naturally, anytime you change structure, you'll affect physical properties as well.
Yeah. Sometimes just by looking at the color chain, you will see the change of the water binding, right?
Right.
Yeah, the next question I think is more industry related. Can we replace zeolite with MOF for industrial process such as hydrocracking, heavy hydrocarbons to value-added products?
My short answer is no, and nor should we try, because
Yeah.
zeolites are fantastic at what they do, and we should also stop trying to replace zeolites with MOFs. I think a better way to think about MOFs is, what can they do that other solids cannot do, right? And this is also something that I think was propagated early on in the MOF field, where, they're like, oh, it's kind of like zeolites. They're not. The only thing that they have in common with zeolites is that they're microporous.
Yeah,
Right.
I agree. We should find some other particular application where the MOFs are super good at. Next question from the Rabia. What other strategies can be employed for the absorption of some inert gases by MOF apart from functional group and pore size regulation? Inert gases, probably nitrogen, methane, or even, I don't know, any ideas?
I mean, I guess I would calling functional group is if you include metals and things as well as organic fine. That kind of covers a lot of the tricks that we have in the MOF world. Like Mircea showed some, these open metal side MOF, different structures. I mean, that kind of covers a lot of ground just saying using functional group. I think that can cover a lot of possible approaches, like, people for nitrogen, for example, metal back bonding has been shown to be a way that you can bind it strongly. Methane, looking really carefully at pore structure and hydrophobicity is a great way to bind it with high capacity and strongly. So I think functional group is covering a lot of ground in that question. I think that's really that's what we have is the organic functionality of the linker, but also the chemical identity and structure of the metal nodes. That's all sort of tools that we have to make absorption better. I would call that all kind of like functional group manipulation.
Thank you, Fa. And I think the next question is also for you. Ke asked a question, how about the recyclability of your MOF material as a catalyst?
Oh, yeah, they are. We found that for most of those reactions, as exotic as they seem, the MOFs tend to survive them with no problem. I think this is getting back to Mircea's other point he raised, that MOFs have a terrible reputation. I could agree. Outside of the MOF community, they absolutely do. And we have to be ambassadors to tell people they're not like these super fragile solids that decompose when they smell air, right? A lot of times. So most of the MOF that we studied for all those reactions, it survives all of them at the end and can be reused potentially. Yep.
Yeah, great. Now come back to the MIP. The Sherman gave a definition is a molecular imprinted polymer. So the synthesis of the molecular imprinted polymer in the presence of the quantity of the MOF zirconium affect the structure of the MOF in the composite material obtained. Not sure if you guys have any experience in MIPs. Yeah, so sorry, Sherman, you are highly recommended to come to the MOF conference. I'm sure your question will be answered during the conference. Zhongqi asked a question, is it possible to make the zirconium serum by a metallic porphyrin MOFs with tetracarboxyphenol porphyrin as a ligand? I think that is for Connie. Connie?
Quite possibly. We have not yet tried that. So far, our interest has mainly been on trying to modulate the distance and spacing and orientation of the rhodium centers.
Yeah.
Cerium could be interesting to see. It often builds similar nodes to zirconium. So I would say with enough optimization, I would imagine that would be possible.
Yeah, thank you. All right. Depanka asked, you think the MOF is going to be one of the best options in water treatment? Well, I think that depends on whom you talk to, who is going to answer this question.
I think Phil should answer this question.
You're the one who has studied water absorption in MOF. It seems like there's some promising stuff going on. I don't know if it might be too early to tell, might be the answer here. It's certainly a new avenue, I think, for MOFs, where water harvesting, for example, from air is only something that's started to be studied in the last few years. Water purification, I think it's still probably too early to say for sure if they can beat, for example, polymers and polymer membranes, which are kind of the leading materials in those areas. So I think my answer would be it's too early, but I think there's potential there.
Yeah, in the interest of time, we'll just take one more last question from Xiaolong. Interest in the single crystalline 2D MOFs are really difficult to obtain, which I agree. Are there any efficient ways to produce large size 2D MOFs to fully characterize the structures? Oh, that's a tough question.
If you figure it out, let us know. It is very difficult to do, and in our lab, we've tried some things and struggled with that. So I think it is a hard question to answer, and it's probably a trial and error. Mircea probably is the person who's a better answer than me. I'm just wanted to tell my joke.
Yeah, I mean, this is something that, of course, we've tried too in context of other research in our lab. There's no two ways about it. It's very difficult. I think the really optimistic view is that for structural determination, luckily ED, electron diffraction, is now coming online, and it has helped determine, I think, to my knowledge, the vast majority of 2D MOF structures along the conductive ones, at least. So, you just don't need that large crystals. For physical measurements, for devices, obviously it's important to grow large crystals otherwise.
Great, thank you very much. Speaking about ED, we have one-day workshop on the materials characterization, and we have two speakers. They will teach the audience the principles and applications of the ED. So for all of you, if you're interested, I highly recommend you to come and join the pre-conference. Okay, and I also see many questions related with the application, the industry application, scalability, stability, recyclability of those materials. In the MOF 2024, we have the whole afternoon of the industrial forum. So we have invited many companies, many investors, the end users, to come to share with their experience, to share with their viewpoint, outlook of those materials. You will be surprised to see the strong interest from industry on those materials. And there are spin-off companies, there are demonstration pilots using those materials for catalysis, for carbon capture, for water treatment. So I highly recommend you to come and join us in the MOF 2024. All right. So in the interest of time, please join me to thank our three speakers again, Mircea, Connie, and Phillip. Thank you very much for making this webinar a fantastic one.
Thank you. See you in Singapore.
Yeah, thank you.